Okay, ladies and gentlemen. Okay, let's take a look here. What we're doing here. Gonna have to go back. And you guys are gathering data. Okay. All right. So what I'm going to do now here with you guys on this today is the following. Okay. So let's ask you actually a few things. I'm going to have to get that information from you guys here. So what I've kind of titled this, in case you guys didn't know, today we have pictures of data. Okay, we've gathered data. We've organized data. And now we have things called pictures of what? Data. So do you guys happen to remember what were your frequency values here for the ages? It's in your notes. What were the frequencies? Because we're going to start to draw some what? Pictures of data. So give me the frequencies. Give me the midpoints so we can start to do that. Get out some pictures of data. Okay, what do you guys have? What's your frequencies? 13, 6, what is that? 4, 3, 4. Okay. Now, what were the midpoints yesterday? You guys had some midpoints here. 19.5. What else? 23.5. Anything else? Okay, and then what else? And then? Is that 35.5? All right. So, good. Now, pictures of data. I'm going to write this down here for us. Now, there's going to be two pictures that we're going to draw today. One picture is called the what? It's called a histogram. Okay, I'm going to put this in our notes. And a histogram, just to kind of summarize it for you, is this. Right? A histogram, if I draw a picture so you guys know, this kind of borrows from algebra. You got an x-axis and you have a y-axis. So remember, here's your x-axis, and x represents the what? Data. Remember that? These x values are called data values in general. And we don't have a y-axis. This will be our frequency axis. So to kind of remind you guys or draw a little picture, a histogram looks like this. What do you think this is? You guys know what this is? If you had to describe it to somebody, right, or you have to remember what it is, what would you guys say to yourself? This looks like a what? Yeah, this is also called a bar chart. And these bars are actually what? Yeah, they represent the frequencies, but they're rectangles. Do you guys see what I'm saying? How they're rectangles? So you got these rectangles. You got these data values. And I want to say something here. There's no what? What kind of picture does that look like to you as a sketch? Does that kind of look like a cityscape? Kind of. Just like a city, what we call a cityscape. And that cityscape, I'm going to say there's no gaps. Okay? So there's no gaps in the cityscape. What do we call this? This is called a what? A histogram. That's one picture we're going to draw. And, you say, why do we draw pictures? So we can actually I don't know, view what we call the distribution of our data. So we want to see the distribution. We got to get a picture of it. Picture's worth 1,000 words. And then the other picture that's kind of related, very much. Still, it's the same kind of system where you have the data versus your frequency. These are the midpoints. So yeah, I mean, it's the midpoints for everyone. Remember he said, what data value best represents the what? The bins. So you can actually see a picture that looks like this to some degree. Okay. Draw your straight lines. Draw it to the axis. And I want to say this is where you actually plot the midpoint versus the frequency, like plotting in algebra. And of course, you connect those points, you know, with lines, straight lines. So there you go, ladies and gentlemen. You got these pictures of data, all right? This one's called the frequency polygon. Frequency polygon and a histogram bar chart, okay? So we're going to do that here today with this data that we have with our group data. Okay, you guys okay with that? So we're going to draw pictures today. So let's do this here. So we're going to start with a histogram. And before I do that, I'm going to have to give you a kind of a definition here. Okay, because remember, for the histogram, there's no gaps. So I'm going to have to talk about what's called boundary values. Right, so for this histogram, if I went back to the data, take a look. You see these bins? You got the first bin holds data values that are what? So I'm going to get rid of these colors here to kind of emphasize some things. So I have bin number 1. So bin 1 holds data. Bin 2 holds data. Right, bin 3, start to kind of color coordinate this a bit. Bin 4 and bin 5. So the first bin holds 18 to 21, is that right? So if I'm going to start to draw this histogram without any gaps, you're going to see my problem here. Okay? So I guess we have this definition. We're going to bring it up again, but I want you guys to appreciate the issue. 18 to 21 in that first bin, is that right? So I'm going to say to you guys this. You guys want to do this here. Okay? Remember, this borrows from algebra. You know, I know that on the real number line, okay, 18 is not that close to the y-axis. But for this, we're going to put it close, okay? That's what you guys want to do. And then this is where the first bin goes, and the data, this is from 18 to 21-year-olds, and I think I might have used orange for that one, right? And what's the second bin? Do you guys know? That holds 22 to what? And what color? Green, 22 to 25. Green. So as you guys can start to see, when you label the boundary values, I'm sorry, not boundary, the bin limits, and then 26 to what? 30, I think? You should start to see an issue. This is where the third bin would be, right? And then you got what? 31 to 31 2. Did we screw up? 26 to 30, or what was it? 26 to 29. Okay. And then 30 to 33. Okay. 26 to 29. 30 to 33. And then you have maybe 34 to what? 37. Do we have another bin? Nope. Okay. And I think, what was our colors again? You go, oh, you had what? Oh, we had brown, blue, and then purple. So brown, blue, and purple here. And so if you use the things that we're looking at here called bin limits, you would have a real issue, wouldn't you? You say, what are the issues? Well, when you read it, you don't even know if like, for example, over here, if that's 2,122. Okay, see what I'm saying? It's very difficult to read. If this is 2,526 or 2,930, 3,334, they're all very difficult to read. So here's my point. You're going to need to use what we call here. You see that red line? See that red line? See these red lines? I'm going to put a red line out here and a red line over here. Those red lines is what I'm about to define for you. These are called what? Boundary values. This is going to close our gaps. Okay? So we want to close those gaps. We can't have gaps in our buildings. So boundary values, ladies and gentlemen, if I can do that. That's what I'm about to define for you. These are the what? The midpoints between adjacent bins. So these are all midpoints between adjacent. What does adjacent mean? Next to. So I want you guys to focus on this here, okay? This is extremely important here. You don't even have to use your calculator, but you can if you like. If I said, what's midway between 21 and 22? Yes, in your calculator, midway between 21 and 22, parentheses, 21 plus 22, close that, divided by 2. What do you guys end up with? It's 21.5. Is that right? All right. What do you think you just found? The midpoint between bin 1 and bin 2. So I'm going to erase that here, and I'm going to say this is going to be what value? 21.5. Okay. I'm going to go over now to what? 25 and 26. What's midway between 25 and 26? Okay. Parentheses. 25 plus 26. Close that, divide by 2. What do you end up with? What is that? 25 point what? 5. And there you go. 29 and 30. Can you guys find what's midway between 29 and 30? 29.5? Do you have to use your calculator for that? Okay, good. What's midway between 33 and 34? All right, good job. And then, ladies and gentlemen, you might say to me, what do I do at the very end if there's not another bin? Well, I'm going to say pretend there's a bin. What do you mean by that? Start with 38. What's midway between 37 and 38? If there was another bin, what would that boundary value be? 37.5. Okay? But also make sure what? Even though you say, okay, there isn't a bin prior to 18. But if there were, what would the boundary value be? 17.5. So I'm going to label this in red, 17.5. And now, ladies and gentlemen, here's my point. Oops. Better be careful. I can now start to draw my rectangles. I'm going to get rid of all of those marks that represented bin limits. I can now do the rectangles, ladies and gentlemen. Okay. And I won't have any gaps. I'm going to move this over a little bit. Okay, you guys okay with that? So this is how we handle what's called the horizontal axis, and the vertical axis is our frequency values there. So we're going to look at the frequency values and take a look at what's the largest value. It goes up to 13, right? So just to remark about that axis, if the largest is 13, typically we want to draw for the vertical, axis between maybe 4, 5, or 6 lines. So, you're going to have some freedom when you do that. I might say, okay, this is going to be every mark is what? 3, 6, 9, and then what's the next one? 12, and then what comes next will be what? 15. This is going to represent my frequency values. This is the altitude. So for the first bin, we're not going to use bin limits. We use these boundary values because we don't want any gaps. That's what you're doing, these boundary values, midpoints between the adjacent bins. That's what's in red. What was that first frequency? 13. So 13 might be somewhere where? Here. It's more than 12. It's about a third of the way. I even put the 13 number here. And what I'm remarking to you guys here is this, that that rectangle represents the frequency of the first bin. And this is how we start to draw a histogram, a bar chart, rectangles, and that first rectangle has an altitude of 13. We're going to do that for every one of these bins and their frequencies, okay? So the second bin in green, what's the frequency? 6. So I'm going to have to draw a rectangle again. But this time, the altitude is what? 6. And there you go. So what's the altitude for the third bin, ladies and gentlemen? What are you going to do here for the third bin? 4. So I'm going to have a 4 somehow. And you go, well, how does 4 is about what? It's more than 3, right? So I like to label as well. I have to do a height of 4 units, so you guys know. And this is the third bin. That's the altitude of the third bin. It's a 4. And so, ladies and gentlemen, we're on our way drawing our histogram here. Was that right? What's the altitude of the next bin? What's that going to be? Is that 3? All right, so we're going to have to draw a altitude height of 3 now. There we go. And I think that one was blue. Is that right? And there you go. I'm going to color it so you guys can see it. What was the last altitude here? 4. Okay. So I'm going to have to copy that altitude of 4. What color was this one? What was it? Purple. And ladies and gentlemen, you are looking at, and again, this data represents what here? Ages here. So we just drew a bar chart, formerly known as a histogram. Okay. But these bars are the cityscape, doesn't have any alleys, okay? There's no gaps, and that's what you need to do. So on a test, I'll ask people, draw a what? Histogram, and you make sure you what? Use these numbers. What are those numbers called? Nope. Boundary values. Good. What do you guys think? And again, why do we draw pictures of data? What's the whole purpose? Why do we draw these pictures? To view what? To view what we call the distribution of the data, how the data is distributed. And so let me give you guys some language here or some ideas. Let's look at this and let's start to ask you guys this question. When you want to actually consider the picture, or I should say, when you look at the picture, here's what you want to observe. Where, I'll write that down here. And it's not about being creative. Where is most of your data? Where is most of your data located? Huh? Yeah, you can say the first bin is 13. That's right. But I'm talking about as a picture for all of it. It's a very, very simple kind of question looking for a simple answer. You know what I'd say? I think most of the data is on the what? Left. So in some simple way, most of the data is where? On the left. Would you guys agree with that? On the left side, you guys hear what I'm saying? You know what we say though formally? When most of your data is on the left, we say that the data is actually, it's the opposite. It's right skewed. So I want you guys to understand that idea. Even though most of the data is on the left, we say, oh, it's right skewed. It's kind of like, there's not enough data on the right. So this is a picture of what we call what? Right skewed data. Your data is right skewed. All right, easy breezy, lemon squeezy. All right, you guys okay with that? Most of the data is right skewed. Most of the data is on the left. We say it's right skewed. So I'm going to put some notes here. when most of the data is on the right, ladies and gentlemen, we call that something as well. That's known as, what do you think we call that? Left skew. You know, so you can have a picture where most of the data is on the right now. And if you do, we just call that what? Left skew. Okay, and you also have a situation where most of the data is in the what? Is in the center. So where most of your data is in the center, ladies and gentlemen, that's called what? Right, so here's kind of a picture of what I'm talking about. And, you know, we don't want any gaps, so. Well, most of the data is in the center. That's known as something. We say the data is normal. Okay, that's kind of what we know. That's kind of what we feel is a normal situation. So you got left skew. Most of the data is on the right. It's opposite in language. This one's not. Most of the data is in the center. That's called normal. We have a whole chapter on normal distribution. You know, you might say, what is that? Well, do you guys ever see this kind of thing before? What's that called? That's the what? The bell-shaped what? Bell-shaped curve. Most of the data is in the center. Bell-shaped curve. Most of the data here, you know, you say, you can kind of draw this little picture. Most of the data is on the right. That's left skewed. And even over here, most of the data, if I kind of drew this around it, if I could, let me do a better version. Whatever. I think I have to do it this way. Yeah, most of the data is on the left. That's right skewed. So just to kind of let you guys know, we have another situation that can show up. And, you know, it's kind of interesting because sometimes on a test, I'll ask questions like this. How is the distribution distributed, right? After people draw a histogram. And you want to know what I get a lot of times? Some made-up answers. And I'm going to say something about this. What do you think this distribution is? Almost like every bin has what? Same amount. You know what they call that? This is a uniform. A uniform distribution. So what I'm really getting at is, what I'm really looking for is actually a phrase, not a sentence. Nobody's looking for a creative kind of story. Oh, most people sleep late at night, blah, 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 you know, type of thing. No. You're looking for a uniform distribution. You're looking for what? Normal distribution. You're looking for left skew. Or you're looking for what? Right skewed. That's it. That's it. Okay? So those kind of questions, when they want you to describe the distribution, they're nearly not looking for a creative story, if you guys want to know the truth. They're just looking at, do you understand the meaning of those kind of pictures? Right skew, left skew, normal, uniform. That's all. And then there's some distributions that don't have any sort of pattern. And there's no phrase for it. So I might even put on a test like these are your possible answers, and then hopefully people don't guess, but sometimes they do. They'll see a normal distribution and they'll say uniform. I'll see a normal distribution, they'll say right skew, So, but that's kind of what you're really looking for. Do people even know the distribution that they're looking at? That's what you want to test people on, because those are real standard kind of languages and about information about distributions. Distribution is normal. Most of the data is in the center. The distribution is right skew. Most of the data is on the left. Distribution is left skew. Most of the data is on the right. It's a uniform distribution. That's all. All right. This picture, you say, well, why did you draw? I mean, what do we say about this picture? That doesn't look like anything. So it's not uniform. It's not normal. It's not left. It's not right. It's just kind of there's no words for it. Okay, so there's no words for this little arbitrary picture I drew. Okay, you guys okay with that? Easy peasy, lemon squeezy? I don't know. Maybe I should do that. Give people a whole bunch of note to self. Create more worksheets where you have to draw what? Histograms and what? Frequency polygons. Note to self. And then you describe the distribution. All right, what about this one here? I should have done that yesterday. Can't. That was Valentine's Day. Don't work on Valentine's Day. Anybody here work on Valentine's Day? Anybody waiter and a waitress? You are? Huh? At a pizza shop? Is the pizza any good? It is? What's the secret? No? How do you make the sauce? Just curious. Puree. Okay. Interesting. Always making homemade pizza. Anybody make a good homemade pizza? Never tried. You do it in the air fryer? Does it come out okay? Not bad. What do you do with your pizza sauce? You just buy what? Oh. Trying to figure out how to do a good pizza sauce. To me, that's the secret. Good pizza sauce is the secret, in all honesty. And I hate to say it, you guys know what kind of pizza sauce I kind of like? You guys know I kind of like this pizza. I don't know why. Kind of ashamed of myself. Huh? Where? No. I'm not that scandalous. What's that? Well, I remember I have a story about this. It's kind of funny every time I think about it. I actually like Shakey's pizzas. I don't know why. I like Shakey's. I like their pizza sauce. It's like it has a kick and it's tangy. Like, man, this is how you do it. Can't do it at home. But I remember once upon a time I used to teach at a middle school. And these kids are out of control. So at the end of the month, whatever class was the best behaved, I threw a pizza party. And I said, okay, you guys can order any pizza you want from anywhere. I'll buy it from you. You get some good stuff, right? You know what kind of pizza these kids wanted? Not Little Caesars. No. I'm trying to remember the name. It was like, I remember the name even. No. It was like the cheapest pizza you can find. They didn't even use real cheese with this pizza. It was like a horrible pizza. What is the name? Pizza Loca? Yeah. I don't know. They all wanted pizza. That's the pizza they wanted. And I'm like, no, you guys, I'll get you some good pizza. You don't have to get that stuff. We'll get you something good. They wouldn't have it. You know what I mean? I would have gone like to somewhere really good to get some good pizza. They wanted Pizza Loca. I can't believe it. I even told them that's not real cheese. They didn't care. They didn't care. You guys like Pizza Loca? Anybody here? A big fan of Pizza Loca? Oh, we got one. Told you. You like it? Oh, there you go. But if you guys could get the recipe for Shakey's pizza sauce, please let me know what they do, because I would love to do that at home. I don't know. You can make it up. They make it like tangy and spicy. Darn it. Anyway, that's what I remember when I think of pizza. Sorry. Remember that story, Pizza Loca? I was like, you guys, it's not even real cheese. They loved it. Anyway. So my apologies to you guys if you said, well, I love Pizza Loca too. It's like, okay. You like Little Caesars? You guys like Little Caesars? Huh? It's okay? I mean, if you're next to a Little Caesars and you're walking home from school, I don't blame you. Exactly, I don't blame you. Because like, yeah, I'm going to stop by Little Caesars. I don't blame you, but it's like, it's just, I think 7-Eleven pizza's better. You guys don't like 7-Eleven pizza? I know a guy from New York, and he told me, there's a guy I know from New York. If you guys know anything about pizza, people from New York, they make pizza. It's good pizza. They're very fanatical about their pizza. Okay, they're fanatics in New York about pizza. And it is I hear it's the water. So the guy from New York, he told me, says, best pizza in the world's New York. So I'd say, Mitch, how do you know? Of course, he's from New York. He says, well, I go, what's the secret to their pizza? Why is it so good? It's in the water. Like, really? It's in the water. That's what I hear. Don't know. Some pizza places locally will import water from New York when they make their pizza. I forget, there's a place out here in LA that does that. Don't know, but he claims it's the water. What else does he say? Yeah, he's the one who said, you know what? 7-Eleven pizza's not so bad. I said, really? You like 7-Eleven pizza and you're from New York? I said, yeah, no, it's okay. When you order it fresh, he goes, it's pretty good. I don't know. You can order it fresh, but it's not fresh. I mean, recently made type of thing. So anyway, just a little pizza story. Sorry. Apologies to you if you're a fanatic about Pizza Loca. I don't know. I don't know if I found a really good pizza place, though. I don't know. How do we draw a frequency polygon? You plot what? Midpoint versus what? Frequency. So every one of these values is a midpoint for your what? For your bins. So one of the reasons you have to get these midpoints, ladies and gentlemen, and these are all the midpoints, right? So remember, they're what? 19.5, 23.5, 27.5, 31.5, 35.5. So you're going to plot the midpoints versus the what? Frequencies, okay? And be careful because it's like backwards when you see it here, right? It's kind of backwards. So what I mean by that, let's draw again the axis. So what's the first midpoint? I don't remember. What was that first midpoint? Was that 19.5? I do remember that. Oh. Yeah, it's 19.5. What's the frequency? 13. So ladies and gentlemen, I'm going to have to do that little stuff again here. So there's 19.5 here as a midpoint, right? And then here's 3. Here's 6. Here's 9. Here's 12. And then that was 15, but I'm going to have to plot a point there and I label the frequency. That was 13. You guys okay with that? So notice midpoint and then what over here? Frequency. That's your first point, okay? So you plot the midpoint versus the what? Frequency. What was the next midpoint? Do you guys remember? I think it's 23.5. Is that true? Okay, what was the frequency for the second bin now? Midpoint 23.5. What's the frequency? I think it was 6. Was it 6? I'm going to label that as a 6. That is the next point. So let me actually do this too so you guys can emphasize this. Orange and green. So remember I said the midpoint best represents your bin? Orange, what else? Green. Okay. What's the next midpoint? I believe it's 27.5. And what was that frequency? Was it 4? Okay. So I'll plot where 4 would be, and I think that was a gold color. Notice this is your what? It's your midpoint. Okay, next midpoint's going to be what? 31.5. What was that frequency? 3. What color is that? Blue. Okay, so I just want to make sure you guys are plotting the midpoints versus a frequency. And then I got the last one going to be 35.5, I believe. And what was that? I think that was also 4. Is that true? And I forget the color. Purple. Oh. So I'm plotting the midpoints versus my what? Frequency, because that's what this says here. Plot the what? Midpoints versus your frequency. You guys okay with that? These are all the frequency for every bin, of course. And then, what do you guys notice here in the picture? You connect these points with what? Straight lines. But make sure you draw that line to the axes as well. You see, this is a shape called a polygon. It's a closed shape. Okay, it's closed. You say, what do you mean closed? Yeah, this is what I mean. That's a polygon. But it's a frequency what? Polygon. So make sure now with all the points, draw your lines. Right? Straight lines. First straight line, straight line, straight line, straight line. Now draw these down to the axis. And what you guys should see, again, this is going to be the data represents the ages. They're really the midpoints of your bins. Okay. And there's the frequency. Again, what's the whole idea of drawing a picture? so that you can see the what? The distribution, ladies and gentlemen. That's the whole idea. You want to view the what? The distribution. Where's most of the data at? Double check. Look at the picture. Most of the data is on the left. Is that right? So most of the data is on the left. What do we call that? That's known as what again? Right skewed. So your data is right skewed. All right, nice. And this is why you draw pictures of your what? Distribution, so you can kind of now talk to people about that. Oh, the data is kind of right skewed. They go, oh, most of it is on the left. And yes, you know what that kind of means in the context of ages? That means students are actually younger in this class. Most of the students are in the youngish kind of region, right? Because the data represents ages. Okay, does that make some sense? You guys see what I'm saying? Most of the data is on the left there. So yeah. So that's the real reason why you guys draw pictures of data, so you can see it. What do you guys think? Is that okay? Interesting. Let's see. We got some question here. All right. Okay. Anybody have any questions on these things here? Nope. Okay, so notice what have we done so far? We've what? We've gathered data. We have summarized. I'm sorry.